Good afternoon, DEF CON. Our next talk is Zero Trust Total Bust. Please give a big welcome to our next speakers, Dave and Rich.
Hey everyone, thanks for coming to our talk about Zero Trust Network Access. I'm Dave, this is Rich. We both work at Amberwolf, which is a UK-based consultancy specialising in red teaming and vuln research. We're covering a lot of bugs in this 45 minutes, but all of the technical details will be on our blog within the next few weeks, some of them straight after this talk. So everyone's heard of Zero Trust. The theory is that no user, device, or request is inherently trusted. Everything must be continuously evaluated against a set of access control lists. So even if you've got valid creds, you won't get access unless all the criteria are met. There's some terminology that we'll be using in the presentation. If you think of SASE as like the gatekeeper, checking whether the user and device are permitted to access a resource, acting like a traffic controller. And then you've got steering, which is routing traffic based on conditions, so like ACLs. Identity providers feature in this. It's not their fault. And we've included a definition of privacy just as a reference. So the number one question we got asked after our last presentation was, what about ZScaler? And we've all seen adverts similar to this saying that legacy VPNs are dead, need to move to the cloud, zero trust network access. We also routinely see these products on red team engagements, so we thought we'd better take a look at whether they live up to their claims. So picture the scene. Everyone's panicking over the latest Avanti bug and they want to move to ZTNA. So what happened is that people just replaced their VPN with a ZTNA product, but then just used it just like a VPN. So no granular access controls, just brokering connections into the internal network. And actually, even worse, we've seen a lot of this trusted corporate LAN concept used in the ZTNA world. But instead this time, you're sharing an IP space with every other customer of that ZTNA product. So we see conditional access policies like this, where there's an exclusion for MFA from the ZTNA public IP ranges to reduce authentication friction. And this means that we can just bypass MFA by coming from those ranges. A lot of the vendors do have a concept of dedicated IPs, so if you do have to do this, then maybe look at that. But enough of the preamble, let's get into some actual bugs. So Checkpoint's ZTNA offering is called Harmony. We cracked open the Windows client in DNSpy, immediately saw a reference to an encrypted private key within an upload to SFTP function. Interesting. This function is called whenever a customer chooses to upload log files to the Checkpoint support team. And that decode resource function you saw, that just decrypts a resource from within the binary with a hard-coded AES key and IV, and the result is your standard OpenSSH private key. The log files were also encrypted before being uploaded to the SFTP server, but the encryption key was predictable and brute forceable. The log files contained JWTs that lived for 30 days, so the impact is that any customer that had uploaded logs could just be compromised because those JWTs can be used to auth straight to the ZTNA service. Read access to that SFTP file system was removed immediately upon reporting to Checkpoint. That's pretty quick. We've got some more bugs in this product as well, but they are still in disclosure at this point. When we started this research, we made like a little wish list of what are the best bugs we could possibly get in all of these products. So we're going to keep this table updated as we go through the presentation.
So next we're going to take a look at ZScaler, which is a very popular ZTNA product. We see this a lot in red teams. And we'll start from a completely unauthenticated perspective. So the first thing that happens when you launch a ZScaler client is you put in your email address. As soon as you do that, the client's going to start making requests to the mobile API. So the first request it makes is it's encrypted here, and we don't have time to go through reversing the exact encryption routine here, but to summarize, essentially it generates a random AES key, it combines that with a hard-coded key, and then it encrypts that with RSA and adds it to an auth token header, and then that blob that you see there in the post request is encrypted with AES. So we'll just decrypt that now. So you can see here it sends a device type and a user email, and then that uses that to fetch the cloud endpoint hostname. And then the next request is this get AEP. And again, we just decrypt this. And so before you've put in a password, it pulls down this policy pre-auth, and it's called the pre-auth configuration for the tenant. So what does a pre-auth config contain? So this can include configuration details such as the authentication settings, such as whether the tenant is using IDP, or it can contain things like the cloud features that are enabled, whether they're using ZPA, Zscaler private access, or just ZIA, and what features in the ZCC client are enabled. So things that we might be able to potentially abuse once we get a shell for things like privilege escalation. So this has been fixed now, but the pre-auth config also used to contain a URL for the pack file, and this is something that we'd commonly see on red teams. So they usually look something like this one here with lots of misconfigurations in, so it might be things such as like misconfigured wildcards in domains, expired domains, or abusable services like Azure. And what we're looking for here is domains that we can use to bypass inspection, and we can use those potentially for C2. So another way that Zscaler can be configured without the ZCC client is in this explicit proxy mode. So the idea here is that users' traffic is steered to Zscaler's cloud proxies, either by explicitly setting a proxy in their browser or via a pack file. And what happens here is the user's HTTP requests get pushed through the Zscaler cloud proxy. The proxy then checks for a gateway cookie. If no cookie is found, the user is redirected to their IDP to do auth. The user is then sent back through the proxy, and then the proxy checks that gateway cookie and strips that from the request and forwards it on. So it might not be a surprise if we can steal the gateway cookie from a user's device, then we can also authenticate to the Zscaler gateway and make our traffic appear as if it's coming from a Zscaler IP. But what about if we don't have a gateway cookie? Well, unfortunately, we can't show you the next slide because Zscaler asked us to remove it while they fix it. But the good news is we've got a different bug to show you, a better bug. So to pick up where you left off on the Zscaler client flow, if a tenant's configured for SAML auth, the client makes a request to the CL star endpoint. This GET request includes the domain parameter, a code challenge which is used for PKCE, so this is essentially a client-chosen SHA-256 hash, which the user has the plaintext for. And then the server responds with a SAML form, with a SAML request, relay state parameter, fairly standard SAML flow. This is then submitted by the client browser and redirected to the IDP. So once the user signed into their identity provider, the SAML response and the relay state are posted back to this SFC SSO endpoint. This then responds with a 302 redirect, redirecting the client back to the mobile endpoint's test.html endpoint containing a JWT in the redirected URL's CKE parameter. This JWT can then be used to register a device, and that summarizes a typical SAML login flow. But let's take a step back and have a look at that last step again. So the client sends back this SAML response to the Zscaler service provider. The server should then decode the SAML response, extract the user details from the SAML assertion, and validate that the signature is valid for that assertion, for the one that's been configured by the admin in the portal. All fairly standard. However, what we found is that the signature on the SAML assertion was only checked for presence, and it wasn't validated against the IDP's public key. So we could just sign it with any key we wanted, or even one with an invalid signature. So this gives us an auth bypass for any Zscaler tenant using SAML for authentication. So we reported this to Zscaler on the 18th of July, and they were very quick, fixed it within about 4 hours. On Tuesday, the 22nd of July, we tried the POC again, and it worked. So we reported this regression to Zscaler, and they confirmed that they had to roll back the patch due to a more critical issue that was introduced. So this has now been fixed, and there's a CVE, so it's a CVE 2025-54982. And it's fully resolved, doesn't require any interaction by Zscaler clients. So we're going to show a demo of this now. So what we're going to do is we're going to run our script, which is going to forge the SAML assertion. And this contains now, we've got our JWT back, and we've got our code challenge, which we need to redeem the JWT. And then we're going to use our PyScaler tool, which is just going to take that JWT and then register a fake machine in Zscaler. So you can see now in the admin portal, this is our machine that we've registered using that JWT, and you can see the hardware ID that we chose to register with them. So let's take a look at that wish list again. We can tick off auth bypass for Zscaler. So moving on. Another way that Zscaler can be configured was with this authentication mode called device token authentication. So this isn't enabled by default, but it enables admins to allow a token to be distributed to machines or mobile devices that can use Zscaler as the identity provider. This is documented in Zscaler's docs. So on Windows, you simply specify the token and user as MSI arguments during install. But the problem here is that it only validates that the token is valid for that tenant. There's no association with a specific user. So if an attacker or a malicious user is able to extract that token from an endpoint, they can then register as a machine with any username. Or simply by changing the username on an existing device, they can potentially bypass steering policies by simply changing the username and registering as anyone they want. So where is the device token stored? So when installing with the MSI arguments, this actually ends up in the registry. So there's a device token that's stored in the registry in clear text and a username parameter. For mobile devices, this is typically deployed by a MDM config. So we're going to show a demo now of device token extraction and replay. So this is on the victim's machine, so we're going to extract that device token from the registry. And then on our attacker VM, we're now going to import that token. So we're going to pause Zscaler. We've then imported those tokens and username. Then we'll just kill Zscaler so it picks up that new token. So you see now we're logged in as user 1 with just the token. Now if we try and access the internet, we can't get to the internet because this user doesn't have internet access. So let's try a different user. So again, we suspend it and we'll just go in and change the username in the registry. So we'll try admin 1, they've probably got better access. Registers as admin 1. You can see now we've got the network admin policy and we can access the internet.
So move on to Netskope. We came across this on a red team engagement, and it seemed quite architecturally similar to Zscaler. There's a couple of specific bits of terminology to talk about here. So we've got an org key, and that's assigned to your tenant. It's immutable, so it's always going to be the same one. And we've got a user key, which is assigned to the user, also immutable, so always going to be the same for that user, not revocable. Recon, again, very similar to Zscaler. The tenant name's sent, and if the tenant's configured to hand off to another identity provider, a SAML request is returned, and that contains the org key. So we've already kind of leaked that at that point. If they're not configured to use SSA, then there's a high chance that their kind of customer admin portal bit is. So if you go to like customer.goscope.com, there's the same kind of SAML request flow, and again it leaks the org key. So I think we've established at this point that the org key isn't really a secret value. Recon, again, very similar to ZScaler. You can use this org key to pull parts of the tenant configuration or the pack file, and this is before you supply the password. There's actually more information that's leaked through Netskope than there is through ZScaler. You can see some of the endpoints there. And you can kind of get the steering config and everything before you've even supplied creds. We're going to go through the flow of a publicly disclosed authentication bypass in Netskope to set the scene for kind of what comes afterwards. So here we start with our first request, exchanging our knowledge of the tenant name for a SAML request. And remember, that SAML request contains our org key. As is convention, the next step sends the SAML request to the identity provider, and the SAML response is received. So it's all fairly normal so far. That SAML response is exchanged for a JWT. Again, all fairly standard. Then the org key and the email address are exchanged for a user key. And that, as we said, that user key is just a long immutable string that's tied to the user. But hang on, this request has got no authentication at all. We can just see that we're supplying the org key that we have already leaked and an email address. So in actual fact, we can skip that whole SAML IDP stage and go straight to pretending that we're whoever we want, providing we know the org key and the valid email address. So we're McLover. The authentication flow then continues by exchanging the org key and that user key for a configuration, and finally ends with exchanging that same information for a certificate that's used to set up the tunnel. And remember, this is for Netskope's private access solution, which in the scenarios we came across was equivalent to VPN access to the target network. So we got our exploit working, exploited the bug on the red team, network access, reported the issue to Netskope, pointed out that it had already been reported, fixed, and even had a CVE advisory. So firstly, big props to Sander DeWitt for being the original discoverer of this issue. We're a bit confused because if it had been fixed and had a CVE, why were we still exploiting this a year on? But I suppose the important takeaway is that Netskope's recommendations here are use secure enrollment and make sure you use, make sure you use device compliance so that rogue devices can't connect.
So we'll just talk through the fix for that quickly. So according to Netskope's advisory, this issue was first reported to Netskope by the original discoverer on the 18th of April 2024. They released an advisory on August the 26th, 2024, and assigned CVE 2024-7401. So this describes a new enrollment method called secure enrollment, and this was first introduced in release 116.10. So interestingly, in this advisory that they released, it also states that the issue was exploited in the wild by bug bounty hunters. So despite a CVE and advisory, orgs are still running this mode in February 2025 when they made secure enrollment the default. And even now in August 2025, we're still finding organizations who don't have secure enrollment enabled. So what about secure enrollment? How does that work? So this uses a secure enrollment token, and this has to be deployed via MDM to users' devices before registration. As a side note, we're not really sure why they didn't go for just validating the JWT that you could get in the auth flow, but we'll go through it now anyway. So we can see they've added an authorization header here, and this authorization header contains a JWT, and we're still specifying an org key in the URL, but we've now got this signed JWT in the authorization header. So how is this JWT made? It's signed with the secure enrollment token, and it contains the UPN and the user key, along with the org key and in the JWT as claims, which you can see on the right here. As mentioned, this JWT is signed using the secure enrollment token with HS256, but there's also an org key in the URL. So which one will the server use? The one in the JWT or the one in the URL? There's only one way to find out. That's right, get parameter wins. The server only checked the JWT was signed correctly for the org key within the JWT itself, but it actually uses the org key in the URL when it enrolls into the tenant. So if we supply a valid JWT for any Netskope tenant, and then we can tamper with the org key in the URL and begin secure enrollment process for any other tenant. This negates the need to know the secure enrollment token for the target org, as long as you have an enrollment token for an entirely different org. And we can specify the target user in the signed JWT. We even found leaked enrollment tokens online, so you don't necessarily need to be a Netskope customer to exploit this. So what about the fix? We reported this cross-tenant bug to Netskope on the 14th of March 2025. They released a server-side fix in version 126 on May the 12th. This fix now checks that the org key in the URL matches the one in the JWT. Unfortunately, there's no CV for this vulnerability. Despite Netskope being a CNA, they don't issue CVs for server-side fixes. So we're going to show a demo of the cross-tenant exploit now. So the attacker's going to run a script, and they're going to provide the target tenant details, the EPN for the target tenant, and the org key for the target tenant, which, remember, can be leaked pre-auth. They're going to provide the org key and the secure enrollment token for the source org, and then this gets back a cert and a branding file. Then on the attacker's VM, they can then just import this, the branding file and the cert. So now we just restart Netskope. And now we have MPA access. So that's Netskope auth bypass completed.
So we've seen how secure enrollment can be bypassed, but how should it work? As Rich said, it's usually kind of rolled out via MDM, like an Intune install argument or SCCM or something. The token's then stored in the registry in this location, and it's encrypted using DP-API. But it's encrypted using flag 4, which equates to local machine, which in fact means that any user on the machine can decrypt it. It does have a little bit of entropy, and that's hard-coded as this is global entropy string, and yeah, that really is the entropy. We'll just show a quick demo just to show that, yeah, you can actually extract that string as a low-priv user, and what you end up with is the decrypted enrollment key. That's what an enrollment key looks like. So what does all this mean? If you're a Netskope customer and you're still using IDP mode, there's still a complete auth bypass for enrollment. In secure enrollment mode, this has been fixed. But if your secure enrollment token is leaked, for example, from someone compromising your Intune environment and getting the install arguments, then you can still auth as any user and bypass steering restrictions. And it's still possible if you've got an org key, which is very easy to obtain, to do loads of recon on a target environment. So we cover the auth bypasses. What if you've already got a shell? If we're up against EDR, we might want to spend as little time as possible on a monitored endpoint. And actually a good option is to steal the ZTNA config, move it to our machine, and then we can access the internal network from a non-monitored endpoint. So both ZScaler and Netskope can store their configs as DP-API encrypted blobs. Only ZScaler actually does this by default. But in theory, zero trust should stop you from stealing a config. The posture check should fail. The hardware ID should mismatch. But as we'll show, all these checks can be spoofed. So we'll have a quick primer on the ZScaler config. It's stored in a file, and it's encrypted. Well, it's XORed with a fixed key after some kind of convoluted XOR shuffle. But to dump the config, you do require a system. And that means we need at least admin privileges to read it. Luckily, we've got 2 privesks in ZScaler as well, one of which we reported in 2023 and still isn't fixed. We could actually do like a whole other talk on the privesks, but we don't have time to like cover all the technical details in this bit. But we do have some demos to show you in a second after we've explained how they kind of roughly work. But if we go back to our table here, we can tick off config theft. So about these privesks, all of the ZTNA products we looked at shared a very similar architecture. They've got a low privilege system tray and a high privilege service or broker. And those two kind of communicate via IPC. That might be TCP socket, a named pipe, RPC, but they all had one thing in common. They failed to properly validate the calling process. There's some attempts to do this by checking signing or path-based checks, but you can bypass that by injecting into a relevant process. And there's also some kind of tamper-proof stuff, but we bypass that too. But just because you can call IPC methods, that doesn't automatically give you a system shell. But luckily for us, every product we looked at had a vulnerable IPC method that we could exploit to run Coda's system, whether that was directly via like process starting or via file writing. So I'll show a couple of quick demos. Here's our Netskope LPE. You can see the attacker's using a custom IPC client, injects a TCP proxy into a legitimate process to bypass the path signature check. And then after this, the client actually enrolls NACHO VPN style, if you've seen that, into a malicious server, and it gets delivered an MSI update, and that MSI update gets run as system, and ping, we've got a system shell. So next up we've got ZScaler. This is version 4.7, which I think is the latest. Again, using process injection to bypass the signer check and then trigger a vulnerable RPC method to load some malicious code. And then once we've got our system shell, we can dump the user's config, as we previously discussed. And then finally, we use a script to dump the various source values needed to spoof the hardware ID, which will be important later on when we discuss hardware ID spoofing. So back to the wish list, we can tick off Privesk, and this is starting to look quite scary now, but let's carry on.
Cool. So you've stolen config and you've enrolled. Now what? So we mentioned at the start of the talk that zero trust involves verification of the device as well as the user. And one of the ways that this is achieved is through proster checks. So these have been around for decades in SSL VPNs as well, and they're really no different in the ZTNA space. So the specific checks that are carried out vary vendor to vendor, but they typically involve the ones we've listed here. In the ZTNA products that we assessed, the posture checks are retrieved over HTTP from the ZTNA server before being processed locally via the ZTNA client, and then the results are returned back over HTTP to the server. For Netskope, bypassing these checks was really simple. We just had to put an intercepting proxy between the client and the server and change status equals false to status equals true, and we could bypass the posture checks. Whilst this was mildly amusing, in practice, having an intercepting proxy between the client and the server is impractical due to things like DTLS and mutual TLS. So we took a different approach here, and instead we injected a DLL into the client and then used API hooking to spoof the checks at a Windows API level. So another piece of information that we had to fake was the hardware ID. The hardware ID is essentially a hash of information that's derived from various components in the operating system and hardware. And then this is sent during registration and later on during keep alive or device assessment requests. It's supposed to be unique per user and per machine. And if the hardware ID mismatches, the server might refuse the connection or class it as a new device and force re-registration. In reality, all of the values that make up a hardware ID can be spoofed, and we can generate the correct expected hardware ID. In the game cheat world, this would be called a spoofer, and it's really no different for ZTNA. So we quickly realized this would make a great generic tool for tricking software that evaluated these various operating system components to trick these compliance checks. So we made this configurable DLL that could be injected into the ZTNA process and allow us to hook these API calls. For hooking the Windows API methods, we mainly use minhook, because it's a simple library and it's widely used. For DLL injection, we mainly use the app init DLLs. method for DLL injection, but we also have the option to use a signed driver. So for most checks, a simple Windows API hook was all that was needed. However, to spoof some other checks, things are slightly harder. So one of the things that normally makes up the hardware ID check is CPU ID. So they use this as a way to get a unique fingerprint of the hardware. And the way this works is they'll execute the CPU ID instruction to extract the processor info and the feature bits by saying EAX to 1 and then executing the CPU ID instruction. So we can't hook this because it's an instruction. It's not a method. So instead what we do is we use the PageGuard hook. So the way this works is we search through the memory and looking for these CPU ID instructions, and then we find the page that they're in. We set the page as PageGuard, and then when that instruction gets executed, it triggers an exception, which we can catch with a custom exception handler, and then we can swap the register values out just after the CPU ID instruction gets executed. The downside to this is that it's slightly slower than an inline hook. Another option would be to use a custom hypervisor to spoof this, but in reality, we didn't need to do this. So we then created this small GUI application to control the hook settings, allow us to spoof all these various values dynamically, and this allows us to import the config, and it will automatically adjust the spoofing settings to the posture profile inside the config. Although some vendors offer the ability to perform cryptographically verified compliance checks or server-side checks, they're not turned on by default, and some vendors don't actually support this feature at all, meaning that compliance checks can always be bypassed in this manner. Also, we got a side note here that we called it RedScaler, but it makes more sense in British English than American English. Otherwise, I guess we would have called it Rescaler. We're going to do a demo of this now. So this picks up where we left off. So we privest, we stole the config, and this is what the config looks like in plain text. So you can see it contains all the posture checks. So now we're going to import that config into our RedScaler GUI. Just going to re-encrypt the config and put it in the right place. You can see here it's picked up some of the posture checks and asked if we want to apply those automatically. Then it restarts ZScaler. And we're logged in. But we can't get to the internet. Oh, it's okay, we forgot to spoof BitLocker. So we'll just spoof that. Just to show you the posture checks are working. You sunk my battleship. That's a full house for all the products we looked at, bar the checkpoint side quest.
So let's have a couple of minutes on this privacy thing. So due to the way these products work, they have to install a RCA in order to inspect TLS traffic and provide you some of the security benefits that they offer. They're quite long-lived here, like 2065 is quite a long time for a cert. The way these are pushed down are typically either with the policies or they're installed with the client. It's not really particularly different to a traditional VPN appliance or a web proxy. But the difference here is that the zero trust engine is very much an unknown. Your traffic enters there, it's decrypted and processed, and it leaves again. You're trusting that it's routed correctly, that nothing else happens. And we're sure this hasn't happened, but the compromise of a ZTNA provider would allow some additional processing to be performed on the decrypted traffic, and you would never know.
So we'll talk through a couple of defense and mitigations here. So the most important one is if you are a Netskope customer and you're not using secure enrollment, please enable it now. Also ensure that clients are always updated, even if there's no CVE published. Just because there's no CVE doesn't mean there's no bugs, so make sure you're always up to date. Enable cryptographically secure checks or server-side validated checks where they're supported. As far as we know, there's nothing for Netskope, but ZScaler do support this since version 4.4. We've also shared some general hardening tips here and some mitigations to help limit the impact of config theft, for example, requiring re-authentication with a small re-authentication period. And to minimize the attack surface for privilege escalation, disable client-side access to features such as debugging and verbose logging. And finally, if you do use app-based or domain-based steering bypasses, ensure that these are appropriate and narrowly scoped, and they're reviewed on a regular basis. To detect malicious behavior, you can look at vendor-provided logs for newly registered devices that perhaps quickly switch from passing failures and passing posture checks and failing posture checks, and make sure that you're ingesting these logs into your SIEM. You might also see devices coming from unexpected locations or from unexpected operating systems. So for example, if a user normally uses a Mac and then suddenly enrolls a Windows device. You can also use EDR to detect activities on endpoints, such as reading sensitive registry keys or files. And some of the techniques we've discussed require process injection, for example, bypassing those signature checks. Equally, some vulnerabilities might cause the ZTNA process to spawn an unexpected child process. So using EDR to detect on unexpected child processes can be useful too. So there's a couple of techniques that are good for detecting token and config theft. Google have this brilliant blog that explains how to configure auditing for DPAPI events. This is actually aimed at detecting browser cookie theft, but also applies here. So if the data is flagged as auditable during encryption, then the 4693 event will be raised during decryption, or when an attacker attempts to decrypt the value on the machine. But unfortunately, none of the vendors actually flag the data as auditable when it's created, so we can't use this 4693 event type. However, we can use the very, very memorably named Microsoft Windows Crypto DPAPI log if we turn on debug logging. And this is also detailed in the Google blog. And then this gives us a new event ID 16385, and we can use this to correlate the data description and the caller process ID to identify any potential misuse. So in the case of ZScaler, you can see here, when we stole the ZScaler config earlier, you can see the data description is client configuration, which is the description that's set by ZScaler during encryption. Another option for auditing access to sensitive registry keys and config files is to configure SACLs, which will raise another event in the event security log. So this is event ID 4663. And you can see here the event that was raised when we exported the secure token from the registry for Netskope. So in conclusion, well, it turns out there are no magic ZTNA beans. We've got the same old bug classes reimagined for a new technology stack. Rather than zero trust, we're actually putting a lot of trust into these vendors and to process our data securely. And we expect them to clearly and effectively communicate when they do fix vulnerabilities, even if those bugs are server-side, so that clients can make informed decisions regarding risk profile. When the bugs exist only in one place, though, at least patching them is efficient. But even in that case, if the patch still requires you to change a setting, we think that this could be communicated more effectively. Vendors are still putting far too much trust into client-side components, as we saw with authentication bypass and posture profile bypasses, which doesn't really fit the zero trust principle. In summary, we found that in practice, rather than being never trust, always verify, we found it was more always trust, never verify. So thanks for watching our talk. We hope you enjoyed it. We've got a link here to our blog. We'll be publishing write-ups over the next few weeks and days, and you can come up and speak to us and we'll take some questions.